Good morning. I'll start today's topic on shaft design. So shaft design is basically you are considering size, spacing, tolerance, material, deflection and rigidity. Stress, strength, fatigue, reliability, all those parameters also should be considered. Simply supported shaft with two masses in the first and second critical speed. Masses are large compared to the shaft speed. So simply supported shaft with two masses, let's say this is simply supported shaft and masses are there. Okay, then critical speed will be changed. How the critical speed will change, I'll show you. Let's one shaft is here and this is your fixed element. Okay, and mass m1, this is m2. Okay, now because of bending, it will be happening like this. And mass is here, mass is here. Okay, so WC is critical speed. WC is your critical speed, critical angular speed. Critical angular speed. Gamma is your static deflection at the location of the mass. Okay, and G is the acceleration due to gravity. Omega 1 is the critical speed if mass m1 is present. Okay, then the expressions will be like WC equals root over G y 1 by omega c square, 1 by omega c square equals 1 by omega 1 square plus 1 by omega 2 square plus 1 omega 3 square. Okay, omega critical. So combined critical speed will be calculated like this. Okay. Now here in the previous slide you can see if I have a shaft is facing like axial load, it can have torsional load, it can have transverse load or bending load. Like shaft will have its own weight, so it will have sagging tendency. It will have some pulleys or gears mechanism, so that shaft will try to bend or it will shear. So we'll just try to discuss how to design using all these forces. So in ASME document, they're saying like 50 to 9% of all mechanical failures are due to fatigue failure. 50 to 90% of all mechanical failure of shaft, is fatigue failure. Now we have seen shaft material. Okay, we have seen there are several types of materials available for shaft. So few shaft material, common shaft material you can remember C45. It will have ultimate tensile strength 600 to 750 Newton per millimeter square, UTS, ultimate tensile strength, and yield strength will be 380 Newton per millimeter square. So similarly we have other materials C40, C50, etc. So if I give any problem, normally I'll give the values, so you don't have to remember, but you should have rough idea what should be the values. In exam, if something goes wrong in writing digits or putting point or zeros, so you should have some idea that it may be out of range of the values. So shaft can be simple tension, can have simple bending moment, combined torque and bending moment, combined axial loading. So several types of loading will be there. So loading will be like simple torsion, bending moment, combined torsion and bending, then combined axial loading will be there, torsion will be there, bending will be there. Okay, so this sort of force can be there when we are working with shaft. So subject to simple loading, let's say simple torsion. If we have simple torsion, the shear stress, shear shear strength tau equals 16 mt pi d pi small d for solid shaft, and equals 16 mt do pi do square minus di d power 4 for hollow shaft. And the parameters mt torsional moment, Newton per millimeter, d dia millimeter, and do outer dia solid shaft, millimeter solid shaft, do outer diameter hollow shaft, di inner diameter millimeter hollow shaft, tau allowable shear strength, (0.5 to 0.577 into sigma y. Now shaft subject to simple bending. Simple bending. In simple bending, what happens? Sigma b, the maximum stress, max stress equals sigma b equals 32 mb pi dq solid shaft, and equals 32 mb do pi do power 4 di power 4 hollow shaft. Okay, mb is your bending moment, mb bending moment. Okay, now combined loading. Bending, combined torque and bending. So in that case, tau max equals half sigma b plus 4 tau square per half equals half into 32 mb pi dq square plus 4 16 mt pi dq square. Okay, so maximum shear stress theory. Now simplifying, tau max equals 16 pi dq mb square plus mt square per half solid. So solid shaft. Now for hollow shaft, it will be 16 mb square plus mt square half divided by pi do cube 1 minus di by do power 4 hollow. Okay, now from solid, okay, design shaft for rigidity. So angle of twist, theta. So theta equals NPTEL-NOC. So J equals polar moment of inertia. Equals pi by 32 d power 4. G equals modulus of rigidity. The shaft material. L equals length of the shaft. Okay, now theta equals 584 LMT G d power 4 solid shaft equals 584 LMT G do power 4 di power 4 hollow. When the value permissible shear stress tau and allowable stress to theta is specified, the limiting length of the solid shaft theta equals to MTL by GD. So whenever you're designing a shaft or any machine element, so you have to consider fatigue loading. Fatigue loading is how much alternating cycle you are applying on machine element. For example, you have one axle or shaft, let's say shaft, and it is hanging. So let's say one moment shaft is getting load here, this upper layer is getting tension, lower layer is getting compression. Now after 90-degree turn, after 90-degree, what happens, that another layer will be in tension, another layer will be in compression. So the layers are getting alternating compression and tension. Upper layer compression, again after some time upper layer getting tension. So compression tension happening. So there is a fluctuating or cyclic loading. When cyclic loading is there, the machine life will be lower. So in material science, fatigue involves initial propagation of crack. So whenever you have continuous cyclic loading, alternating loading here, so possible that there will be some crack development somewhere and system can fail. And because of fatigue loading, how your life is reducing in this figure you can see. So gradually this fatigue load strength is going down, okay, with increasing number of cycles. Number of cycles means how many times it is getting load alternating. Okay. So stress concentration, a point where stress is significant higher than its surrounding. This occurs due to irregularities in the object's geometry or material, such as holes, grooves, notches, disrupting stress flows. And non-dimensional factor called stress concentration factor is used. For example, you have one shaft, okay, and you have small crack here. What is happening? The total area is here A pi by 4 d square. But at this location, the area reduced actually, okay, A dash. So here my diameter is maybe d dash. So area became pi by 4 d dash square. Okay, so what is happening? So if force is same, let's say this is applied force, okay, then stress development will be like this, F by A. Now in second case, where crack got developed, so their area reduced. Area reduces means P increased. So crack developed implies stress increased. Okay, so any micro crack also, it will increase stress concentration or stress level at a specific location, so that will lead to further growth of crack and will fail. In many cases you have sharp, let's say, bend, so your stress concentration will be there at the neck area, or if you have any bend like this, your stress concentration will be here somewhere. So stress will be concentrated in certain area than other areas. When stress is concentrated in certain area, so that area failure probability higher. Whenever you are designing a shaft or any machine element, you have to check where stress concentration possible or where the weakest position possible on a shaft or any machine element. So the weakest portion, if you can identify, design that one, check that one if that is safe. If that is safe, then other portion will be safe anyway, because you are considering that is the weakest area. So ductile material allows localized plastic deformation at stress concentration. So it redistributes the stress, so failure probability and its safety will be better. But if you have any brittle material, if there is any micro crack, so crack will be propagating quickly and failure will be quicker. Okay, so normally this bicycle and other frames will be made of mild steel, so that if any crack is there, it will be distributing the stress concentration, the stress, to other nearby zone, so system will be safe. But brittle material will not transfer, it will keep just growing the crack and it will fail. Fracture modes, whenever you are talking about failure shaft or any machine element, then you have to see what are the different fracture modes. So there will be ductile fracture mode, brittle fracture mode. Ductile fracture means you are having one specimen and you are giving lots of pulling action. Because of pulling, let's say rubber band, if you pull, what will happen? Initially it will create some narrow area. So narrow area created means narrow area reduced. So same force you are applying but area reduced. What will happen? Stress will be increasing. When stress increasing, further it will be creating necking. So this is called neck formation. Okay, the small area you are creating, so neck formation is there. So neck formation means stress increase. So stress increase means that area will be failed. Okay, but in brittle material, the neck formation will not be there. Okay, no neck formation. Okay, because of no neck formation is there and you have a small micro crack, so micro crack will be giving your stress concentration. Because of stress concentration, it will fail and it will not give any warning. But in ductile material, it will give warning because it will be elongating before it fails, and so you will know, okay, it's getting elongated or neck formation is happening, so you have to take immediate action. Brittle material will not tell that one. It is having some stress concentration, it will fail immediately, done. Okay, so brittle fracture, crack propagation without significant deformation around the crack tip, leading to rapid material failure. Ductile failure, plastic deformation will be happening before failure. Okay, if you see the stress strain curve, strain, stress, okay, so proportion limit is there, then ductile material will have lots of transformation, like it will be elongating, then it will fail. But brittle material, done, break. Okay, there will be no indication of long zone where it is getting absorbing energy and it is giving indication that it will fail. Brittle or ductile fracture depends on factors such as stress level, loading type, static cyclic strain, pre-existing crack or defect, material properties, environmental and temperature. So same material will be behaving brittle or ductile based on temperature also. At very low temperature, certain material can be brittle, but normal temperature maybe it will be ductile. So that also will be affecting. Now we'll try to solve some problem. A key is having square cross section of side d by 4 and length L. Okay, is used to transmit torque T from shaft diameter D. So I have one key here, shaft is here, so my shaft is like this. Okay, so diameter, shaft diameter is D, and cross section area d by 4. This area, this is square shaped, this is d by 4, this is also d by 4. Transmit torque T, diameter D, transmitter diameter pulley hub. Assume that length of the key to be equal. So length also we have to calculate L equal to the thickness of the pulley. So pulley thickness T, pulley. Okay. The average shear stress developed in the key. Shear stress. How much you have to calculate. Now, so torque T equals P or F into D by 2. So let's say this is force is F. So torque is F into D by 2, implies force equals 2T by D. Now shear area will be this one. So this is your shear area. Okay, so this area is just shear area. So shear area equals D by 4, equals D by 4 into length of this key L. So LD by 4. Now shear stress sigma S equals F by A equals 2T by D, F value divided by A value is already calculated, LD by 4. So this is giving 8T by LD square. Okay, and if we calculate crushing also, so crushing area will be changing only. So crushing area will be, this one is my crushing area. Okay, this is my crushing area. So crushing area, crushing sigma C equals force by area, force again same 2T by D. Area changed, area is now D, this is D by 4 into half, so D by 8 into L. So this is giving 16T LD square. So let's see another problem on key. A key of 14 millimeter width, 9 millimeter height, and 100 millimeter length. 100, this is 100, okay, millimeters, so I'm not writing unit. Okay, if the allowable shear stress for the key material is 15, sigma A equals 50 MPa, maximum torque can be transmitted. So here torque equals F D by 2. D means shaft diameter, right? This is D, and this is force it is applying. Okay, so F D by 2. B is 14 and L is 100 and D 50. D is given 50 millimeter. Okay, and tau is 50 MPa. So F by BL less than 50. So F less than equals 50 BL. So less than equals 50 into 14 into 100 equals 17 kilonewton. So torque T equals F D by 2 equals 70 into 0.025 equals 1750 Newton meter. A shaft 750 millimeter long, 750 subject to shear stress 40 MPa, sigma shear 40, and has angle of twist theta is given 0.017 radian. G value they are asking, but the rigidity 0.08 into 10 power 5 MPa. Diameter of the shaft D, you calculate this writing like this. So modulus of rigidity 0.8 into 10 power 5 Newton per millimeter square. So 40 Newton per millimeter square. Okay, so mt equals pi by 16 tau or sigma s tau dq. Okay, theta equals mtlgj. So pi by 16 tau dql pi d power 4 32 into g. So equals 2 tau l gd. So this is giving 0.017 equals 2 into 40 into 750, 0.8 into 10 power 5 into d. So J equals polar moment of inertia for solid shaft. Okay, so this is giving D equals 44.11 millimeter. So problem 4, here marine engine producing 500 kilowatt power and shaft speed 1000, the propeller efficiency 75%, 20 knot speed, permissible shear stress also given, direct axial load. Okay, it is asking to calculate axial load. So power P equals 500 kilowatt. So whenever you are writing kilowatt, write K small, W capital. Okay, so this is standard practice. N equals 1000 RPM, eta equals 75% or 0.75. So velocity 20 knots equals 20 into 1085. It is given in the problem. So 6.028 meter per second. So P equals power equals 2 N pi by 60 into torque mt. Okay, so this is giving 500 into 10 power 3 equals 2 pi 1000 mt divided by 60. So mt equals 4.65 Newton meter. Let axial load is PA. P equals PA into velocity by eta. So therefore 500 into 10 power 3 equals PA into 6.028 0.75. So this is given PA equals 62209.7 Newton. Okay, this is your answer. A 750 mm long uniform solid circular shaft is simply supported at the ends and carries two pulleys of weight 2 kN. The pulleys are 250 mm and 500 mm from the left end. A pull of 10,000 Newton vertically downward on the right pulley is applied. The shaft transmits a torque 3000 Newton meter between the pulleys. Assume KB, KT to constant 1.5, allowable shear stress 70. So how to solve it, this one? So first you draw the pulleys and shaft. Okay, so first center line, then shaft is coming here, it is like this, pulley is here, then shaft is going to next pulley, then shaft, Okay, then shaft is passing through two bearings. Okay, now C, D, A, B. A and B is giving reaction, CD is hanging its own weight. So distance L is 750. So distance are given 250. This is 250. This is 250. This is 2 kilonewton each. Kilonewton, 2 kilonewton. Then it is having force 10 kilonewton. Okay. The shaft 750 long, supported by ends, two pulleys, 250 millimeter, 5 millimeter. Okay. Pull on the right pulley 10 kilonewton, vertically downward. Okay, this is vertically downward. The shaft transmit 3 kilonewton. Okay, so L is given 750. Okay, 750 millimeter. AC equals 250 equals a given in the problem. AD equals 500 millimeter. W1 equals 2 into 10 power 3 Newton. W2 equals 2 into 10 power 3 Newton. MT torque is given 3 kilonewton meter equals 3 into 10 power 3 Newton meter. And shear stress given 70 Newton per millimeter square. And Ka, Kb values also given there. The weight of each pulley 2000 Newton, which acts vertically downward, and pull of 10,000 Newton vertically downward. Now draw the load diagram. Load diagram is like this. Reaction is happening here. Reaction is happening here. So Ra, Rb, and vertically downward 2000 Newton, and here it is giving force 10,000 plus 2000 Newton. This is C, this is D, this is A, this is B. Okay, this is called free body diagram. So okay, free body diagram, how to draw? You have to go to your first year, second year course of strength of material course. Now calculate the bearing moment at all the points. Ra, Rb, reaction force. Okay, so moment about A. About A. Rb, so Rb, how much force will be upward force? So Rb into 750 equals 2000 in C, 2000 in C into 250, not 750, 250 plus 10,000, 12,000 into 500. I mean, because A to D is 500. Okay, so total here Rb is giving 8666.6 Newton. 8666.67 Newton. Okay. Now Ra plus Rb, total force they are holding. So 12,000 plus 2,000, so 14,000 Newton force they are holding. So Ra is 14,000 minus Rb, whatever you got, 8666.67 equals 5333.3 Newton. Okay, so bending moment Bm, bending moment at A. If I take bending moment at A equals 0, okay, because we are taking moment about A, so bending moment is 0. So Bm at C, Ra into 250 equals 533.3 into 250 equals 133. 1.333 into 10 power 6 Newton millimeter. Okay. BM at D RB into 250 equals 8666.67 into 250 equals to 166 into 10 power 6 Newton millimeter. So BM at D, so maximum bending moment occurs at D, implies M bending moment maximum is taken to 2.166 into 10 power 6 Newton millimeter. So equivalent twisting moment MTS equals root over KBMB square plus KT MT square equals 1.5 into 2.166 10 power 6 square plus 1.5 into 3 into 10 power 6 square. So that is giving MTS equals 5.55 into 10 power 6 Newton millimeter. And we know MTS equals pi by 16 tau dq. So this is giving D equals 73.9 millimeter. So this is your answer. Next day we'll start a new topic. Thank you very much.